Hey everyone, welcome to this explainer. Okay, so you probably think of concrete as just that boring gray stuff making up the sidewalk, right? Well, today we're completely flipping that idea on its head. We are diving deep into the highly engineered, cutting-edge world of materials science. By the time we're done here, you are going to see concrete not as some heavy relic of the past, but as the absolute supermaterial of our future.
I mean, seriously, what if I told you concrete could flow completely silently, just like water? Or that it could be engineered to be so unbelievably thin and light that you could actually build a car shell out of it? It completely shatters what we think we know about construction. And that's exactly the real-world stakes of material science. We're solving impossible engineering problems by literally hacking the chemical structure of the materials we use to build our world.
All right, let's dive into this. Here is our roadmap. We're going to start by looking at the monumental scale of traditional concrete, then explore how engineers are literally beating the construction clock. From there, we'll check out a liquid marvel straight out of Japan, discover how we're building lighter with something called ferrocement, and finally take a glimpse into the crazy sci-fi future of concrete.
Section 1. A material holding the world together, the scale of concrete.
Just look at the sheer scale of something like the Glen Canyon Dam. When you're pouring conventional mass concrete on this kind of monumental level, you aren't just fighting gravity. You are in a massive race against time and labor. Traditional concrete usually requires you to shake and vibrate the heck out of it just to get it to settle into molds. And then, you wait. It takes roughly 28 days for it to reach its full design strength. Now, if you're building critical infrastructure or even just residential housing, waiting a whole month for a single piece to cure is a massive bottleneck. So, the big question becomes, how on earth do we speed this up?
Which brings us to Section 2, beating the construction clock, manipulating time.
You know the old saying, time is money? Well, in construction, the fix for these massive delays actually comes down to chemistry and thermodynamics. Think of making concrete kind of like baking. Adding accelerating admixtures is basically like tossing in some superpowered specific spices to your recipe to change how fast your mix bakes. Some of these modern commercial accelerators are so incredibly intense, they can make wet cement set stone hard in literally 5 minutes. It's an absolute lifesaver for emergency repairs, underwater pouring, and cold weather environments where freezing could ruin young concrete. But wait, what if you want to speed up massive, prefabricated sections of an entire building?
Well, when you scale that up into an industrial process, you get steam curing. By putting prefabricated concrete elements into a highly controlled steam chamber, engineers can force a hyper-accelerated hydration process. They use a short initial delay, ramp up the heat, hold it steady, and then carefully bring it back down. And here is the absolutely crucial takeaway. This process allows a precast concrete element to achieve its full 28-day strength in just 3 days. If you've ever wondered how, nowadays, especially in places like Japan, you see entire houses or complex structures going up in just a week, this is the secret sauce. They aren't out there pouring wet concrete on site and waiting a month for it to dry. No way. They are trucking in fully cured, high-strength precast sections that were steam-cured in a factory in mere days and just assembling them on site with incredible speed and precision.
Moving right along to Section 3. Japan's self-compacting concrete, a liquid marvel.
The most revolutionary development in concrete construction for several decades. Now, that quote is not an exaggeration. Back in the late 1980s, Japan was facing a really severe shortage of skilled construction labor. Researchers at the University of Tokyo had a brilliant realization. If they couldn't find enough skilled workers to properly place and manually vibrate concrete into complex molds, the concrete itself needed to do the heavy lifting. They needed a material that was self-compacting.
Now, what's really interesting here is the high contrast difference in these recipes. Old-school concrete needs intense mechanical vibration to shake out air bubbles and force it into corners. But self-compacting concrete, or SCC, totally changes the game. By using a much higher powder content, like fly ash, along with specialized viscosity-modifying agents and superplasticizers, the concrete transforms into a highly fluid, cohesive liquid. It flows completely under its own weight, fills every single tiny corner of a mold, and requires absolutely zero vibration.
Because SCC flows so flawlessly, it easily navigates its way through incredibly dense, congested steel reinforcement, which, by the way, is absolutely vital for earthquake-resistant structures common in Japan.
And when you combine this liquid marvel with that precast steam curing process we just talked about, oh man, it's the ultimate 1-2 punch. You pour SCC into a mold at a factory, it self-levels flawlessly and completely silently, you steam cure it in 3 days and ship it to the site. It leads to way faster construction, thinner sections, a vastly quieter and safer working environment, and those rapid, week-long house assemblies suddenly become an everyday reality.
All right, Section 4, Building Lighter with Ferrocement, the thin revolution. Okay, so we've hacked time and we've solved the flow issue. But how do we solve the problem of structural weight? Standard concrete is famously heavy and brittle. Well, enter ferrocement. Instead of pouring concrete over those massive, thick steel rebar cages, ferrocement uses layers of really fine, closely spaced wire mesh, kind of like chicken wire, soaked in a really rich cement mortar. By distributing the reinforcement so finely throughout the whole matrix, you completely alter how the material behaves. You practically eliminate the microcracking that plagues standard concrete, and you gain incredible tensile strength and flexibility.
And this brilliantly illustrates just how versatile this gets. A car shell made entirely out of ferrocement. Or look at this garden umbrella. It's a structure that is literally only 20 millimeters thick. Because it has such high first crack strength and is so unbelievably light, ferrocement can be molded into incredibly thin, complex shapes, everything from boat holes to intricate folded plate roofs. It absolutely proves that concrete doesn't have to be a bulky, heavy monolith. It can be a highly engineered, lightweight skin.
Which brings us to our final chapter, Section 5, The Future of Concrete, Materials Science Revolution.
Let's examine this incredible array of future super concretes, because honestly, some of these sound like they were pulled straight out of a sci-fi movie. First up, polymer cement concrete. By mixing monomers directly into the concrete and polymerizing it, engineers create a material that is insanely dense and entirely hydrophobic, meaning it literally repels water, effectively putting an end to freeze-thaw damage. Then we have compact reinforced composites, or CRC. By packing the cement matrix with silica fume and up to 20% by volume of ultrafine steel fibers, you get a concrete with a compressive strength of 200 megapascals. That is almost as strong as structural steel, but you can mold it right on site. Next is reactive powder concrete. This completely ditches traditional sand and aggregate, replacing it with fine-ground quartz dust. This pushes compressive strengths to a staggering 800 megapascals, which is exactly what you need for things like nuclear waste storage, where ultimate durability is completely non-negotiable. And finally, bacterial concrete. Yes, you heard that right. This is an emerging biological tech where dormant bacteria are actually embedded into the concrete matrix. When a crack forms and water seeps in, the bacteria wake up and literally heal the crack themselves by producing limestone. I mean, how cool is that?
So I want to leave you with this final, provocative thought. We have evolved from a slow-curing, heavy gray paste to steam-cured precast modules that let us assemble entire houses in days. We've got self-compacting liquids, razor-thin ferrocement shells, and hydrophobic self-healing polymers. What impossible structures will we pour next, now that concrete has truly become a high-tech supermaterial? Thank you so much for joining me on this explainer. Keep your eyes on the built world around you. I promise it's changing a lot faster than you think.